Okay, so today we will start to cover Chapter 3, Conditional Probability and Independence. All right, conditional probability is a unique feature in probability theory. And independence. Okay, independence, it's a spatial situation of conditioning. Okay, and both concepts are very useful in the development of probability theory, as well as the computation of various probabilities. As we know, the core of probability theory is to compute the event of interest, the probability that an event occurs. So, all right. So these two concepts are so fundamental, and we will see how to develop these two concepts. Okay. So we first consider conditional probabilities. All right, so the conditional probability that an event E occurs given that an event F has occurred. And we denote it as P of E given F. Okay. Right? So it's defined as the ratio of the probability of the joint event of E and F. So the joint event, which means that event E and event F occur simultaneously, right, over the probability of event F. Okay? and where it is assumed that the probability of F is positive. Okay, otherwise this ratio will be meaningless. Okay. Okay, so conditional probability of an event F given event F. This concept is defined by this ratio. Okay, and for our purpose, we will consider the special situation that when the given event F has probability equal to 0, then we define the conditional probability of an event E given F, alright, becomes to be the unconditional probability, okay, for all events in the sigma algebra. Okay. Okay. So with this supplemental definition, then the given event F can have probability which is positive over 0. Okay, which is positive 0. Right, and in section 2.5 in the previous chapter, we consider sample space consisting of equally probable outcomes. So if the sample space is finite, and F sigma algebra is said to be the power set of the sample space, and the probability measure P is the counting probability function. Then the probability of E given F, right, becomes to be, we know that this is P E intersect F divided by probability of F if is positive, and this is probability of E if probability of F is 0. Okay. Now, but with the counting probability function, okay, then this joint probability is actually okay. So the numerator is this ratio, and the denominator would be okay. And the probability of E would be d over x so for the first case, when we cancel the size of the sample space, then this becomes to wrong there. The probability of F is positive, which means that the size of F is positive. And this is E divided by S if F is the empty set. Okay? So that's simple. Now, from the definition of conditional probability, okay, so we say this is 3.1 here. And this is 3.1 prime. Right. So this is the companion definition to the previous one. Right. So now from 3.1 and its companion 3.1 prime, we have that the joint probability of E and F, okay, is equal to probability of F times the probability of E given F. Okay. For any E and F in the sigma algebra. Okay. And if we want to give a proof, that would be simple. So we to case 1, that P of F will equal 0 here. Then by 3.1, we know we have that the conditional probability of event E given event F is equal to, okay, and so when we multiply the denominator, so this shows that P of E intersect F, okay, is equal to P of F and P of E given F. Okay, so for the first case, we have this formula. Case number 2, when the probability of event F is 0. Now, since the joint event contained in F, okay, so the probability of E and F, E intersect F, is less than or equal to probability F. Okay, and this is a proposition 2.4.1, and this is XM number 1. Okay, but this is 0. Okay, because here in this case, okay, so you can see by the sandwich theorem, we know probability of E intersect F is also equal to 0. Okay, so that probability of E intersect F equal to 0, and the 0 is equal to 0 times probability of E intersect F. This is the conditional probability, right? This conditional probability, and this is probability of F, probability of E given F. Okay. Okay. So in both cases, that we have the identity here. Okay. Of course, by our definition, this is just probability of E, the unconditional probability, but that's fine. Okay. So we have this formula. Okay. So this formula, we will call it as 3.2. Okay. This formula. So this formula is good for any event E and any event F here. Okay, and use the advantage of this formula is to find the joint probability. Sometimes to compute the joint probability, we can use the probability F and this condition probability. Because in many problems that we know this conditional probability very easily, okay? And then if we know the probability of event F, then this product gives us the joint probability. Now this rule can be extended. Okay. So in general, all right. So we have the multiplicative, or we call the multiplication rule. The multiplication rule says that the joint probability of a finite number of events. Okay, so this is the probability of the intersection E1, E2, and up to En. Okay, so this is the probability that events E1, E2, up to En occur simultaneously. Okay, and so this probability is equal to the probability of E1. Okay, so this is the unconditional probability times probability of E2 given probability of E1. Okay. Okay, and times probability of E3 given E1 and E2. Okay. And finally, the conditional probability of En given E1 and E2 and up to E sub n minus 1. Okay. Right, so this multiplication rule is an extension of the simple multiplication rule in equation 3.2. Okay. And the proof is by induction on N. Okay, and so it's as an exercise. Okay, so I will ask you to prove this multiplication rule. Okay, starting from this simple multiplication rule. Okay. Okay. Now, so from the basic definition of conditional probabilities, now we will see a usage of conditional probabilities, which is the famous basis formula. Okay. Alright, so the base formula is quite useful in the following situation. So I describe that. In many situations, it is difficult to compute the probability of E of an event E. Okay, directly. But it becomes straightforward to compute it once we know whether or not some second event we call F has occurred. Okay? So which means that if we have assigned information, okay, subsequently, if we know whether or not some second event, additional event F has occurred. Okay. All right. So now now a simple decomposition formula is here. First of all, the probability of the event, all right? And now we know if we take the intersection of event E and the total event, we know this is just E. Why? Because event E is a subset of the sample space. Okay, so they will be the set. Now, the sample space is the disjoint union, okay, of F and the complement of F. Okay. So we have that. Now, and we know the intersection has distributive law to the union. Okay. So this is the disjoint union. This is E intersect F, disjoint union of E intersect F complement. Okay. So we can write. So this is sample space. Okay. And this is the event E. Okay. And here. Okay. So this is event F. And this is event F complement. So this is F. The green part is F, and the yellow part is the F complement. So we know the total event is the event F disjoint union, the complement of F here. Alright, and the E, okay, so for this part is E intersect F, okay? And this part is E intersect F complement. Okay. So you see the E itself is the disjoint union, okay, of E intersect F and the E intersect F complement. Okay, so this part. And by finite additivity, we know this is E. Alright? The joint probability of E and F plus the joint probability of E and F complement. F complement here. Alright, and finally we apply the multiplication rule. Alright, so this is P of F times P of E given F plus P of F complement times P of E given F complement. Okay. Okay. So this is implies that P of E has the. So this is our decomposition formula. Okay. So to compute the probability of event E, right? Then if you know that an additional event F, okay, so given event F has occurred, then you compute this conditional probability of E, right? In many situations, this is easy to compute. Also, this conditional probability is easy to compute in many situations. All right, so this is the given F complement, all right, and this is the conditional probability of E. All right, and also you know the probability of F and probability of F complement. All right, so with this, all the information, then you can compute. By this formula, you can compute the probability of event E. Okay, indirectly. Okay, so this is called a simple decomposition formula. Now, with the simple decomposition formula, we will describe the simple base formula. Okay, so is that okay? If we want to compute this conditional probability of event F given event E, all All right, and it seems that this condition probability, by definition, this is the probability of A, F, and the E, and probability of E here. Okay. Right. So by definition, we need to compute this Y. Now, and we find that the probability of E would be a little bit difficult to compute. Okay, and so we will apply the simple decomposition formula, and we know that this is instead we find that this condition probability is much easier to know. Okay, right. So this is by the simple decomposition formula. And for the numerator, we can use the multiplication rule. So the multiplication rule gives us that. Okay. Right? So this one goes here. Is by multiplication. Okay, and for the denominator, we use the simple decomposition formula. Okay, right? So when we apply in these two formulas, we can have the simple base formula here. Okay? Right, so the reason is that to compute this conditional probability, we find that the computation of the denominator P of E is a little bit difficult. Then we can apply the simple decomposition formula. Okay, and from here we know that the first product is actually the numerator, the joint probability of event F and event E. Okay. Okay. All right, and so that to find the condition probability of F given E, we turn around to if we have quite easily to have the condition probability of E given F and the condition probability of E given F complement, as well as the probability of F and the probability of F complement. Okay, then we will have the base formula here. Okay, and the base formula or the conditional probability also related to another concept called the odds of an event A. Okay, so the odds of an event A is defined as the ratio of probability of event A and probability of complement of A. Okay, so that would be probability of A minus probability of A complement Oh, by the way, I should say that provided that with event E is positive. Okay. Yeah, because probability, this probability is in the denominator. Okay, the R is okay, provided that yeah, so just the ratio. Okay. Now it's quite often we want to know, so the odds of an event A may change after a new evidence and this evidence can be described by an event F, I'm sorry. Oh, E, sorry. An evidence E here. So after a new evidence E is introduced, okay. So after a new evidence E is introduced, we have the conditional probability A given E and divided by this conditional probability. Okay. Right. So this is unconditional because we just want to know the odd of an event. So this ratio is defined by the unconditional probability. But once we know new evidence is introduced, so we know the event E has occurred. So E has occurred. Now we have the conditional probability of A, and this one is given the event E has occurred. Now the conditional probability of A complement. Okay. And we have to know that okay, and so we have that. So this is P of A intersect with E divided by probability of E. Okay, so that is the numerator, and for the denominator we have a complement. We have P of E here. Okay, and so we can cancel them. So we have probability of A intersect E, probability A can be intersect E here. Alright, now by the multiplication rule, we have P of A and P of E given A here, and P of A complement and probability of E given A complement. Right? So we have this is the original odds of event A. Okay, comes this vector. So this vector X is here is the ratio of these two conditional probabilities. Okay. So that if you can see the odds, if the odds after a new evidence is induced, if the odds increase, this one is more than the original odds. Even only if this ratio is greater than 1, okay? And which means that this one is bigger than this one, okay? So that when the numerator is greater than the denominator, which means that that the event A, all right, favors the evidence, okay? Right. So when the event A favors evidence instead of and so the event A complement, that's this one doesn't favor the event E. Okay. So we can say that the new odds of the event A will increase if the event A favors the evidence E, and decrease if A does not favor E. Okay. All right. Now we want to extend the simple base formula. Okay. Okay, so we will introduce a concept called partition. Okay. The collection. Okay. So a collection F1, F2, Fn of n events in F is said to be a partition of the sample space S if they are mutually exclusive, okay, which means that if they are intersections, okay, it's the empty set, okay, and their union is S, i.e. The union I from 1 to n if I equal to S. Okay. So partition is like here. This is the sample space, and this is F1, F2, Fn minus 1, F sub n. Okay. So F1, F2 up to F sub n, okay, they form a partition of the subspace. Okay, you can see F sub I and F sub j are disjoint from each other for I not equal to j, so they are mutually exclusive, and their union is X. Okay, you can see that X is the union of F1, F2 up to Fn. Okay. Okay, so when we collect this n event together and satisfy these properties, then this collection is called a partition of the sample space. All right. So now, okay, we call this 3 by 3. Okay, the simple decomposition formula 3 by 3. We first right, so to generalize 3 by 3, we let F1, F2 up to Fn be a partition of the sample space. By the way, we can see here, because of that, so we can see that this collection F and F complement is a partition of the sample space. Okay, so that is simple because you can see the sample space divided to be two parts. One is F, the other is F complement. So this collection F consisting of F and F complement. This one is a partition of X, and with that partition, this is a simple partition. We have the simple decomposition formula. Now, suppose that we have a partition of the sample space which consists of n events. Then, for any event E in the sigma algebra, okay, we have, so we have here, right, E equal to E intersect the X. Yeah. Okay, and because this is a partition of the sample space X, so that X is the disjoint union of F sub I. And by the distributive law, we know that this is E in this the disjoint union of E intersect with F sub I. Okay. Alright, so also you can draw the Venn diagram. So this is F, and the partition, you have F1, you have F2, you have Fn minus 1, you have Fn here. Now, suppose that you have E here. Okay, so you have E. Then this part is E intersect F1. This is E intersect F2. This is E intersect Fn minus 1. And this is E intersect Fn here. Okay. So you have that. Okay. And so the event E is the disjoint union of E intersect F1, E intersect F2 up to E intersect Fn. Okay. So E is this disjoint union. Right, and so the probability of E is the probability. So it comes to the probability of the sum of probability of E intersect Fi. Alright, so this is by the finite additivity. Okay. Alright, and by the simple multiplication rule, so this is F P Fi, and conditional probability of event E given event Fi here. So this formula is the general decomposition formula. Okay. Okay. 4. So we have the decomposition formula here. Right. And so with the general decomposition formula, now we can prove the following proposition, which is a general version of this formula. So this base formula now, so given a partition F1, F2 up to Fn of the sample space X, the conditional probability of Fj given E. Okay, so this is the condition probability of each event in this partition. All right, given event E has occurred. Okay. And so this is probability of F of J intersect E, and this is probability of E. Now we can apply the general decomposition formula. And this one, by using the simple multiplication rule, so this is P of Fj, P of E given F of J. Alright, so we know that this is, for the numerator, we apply multiplication rule. And for here, we use the decomposition formula. Okay? Alright, so the proof of this proposition is quite simple, just by applying the multiplication rule as well as the decomposition formula here. Okay, so let me give an explanation of base formula. All right, so I'll give you a remark. One, events F1, F2 up to Fn are often called possible hypotheses. Since they are mutually exclusive and exhaustive. Okay. Because that different FIs, they are disjoint from each other, so they are mutually exclusive and exhaustive because that the union, their unions is the total event. But in criminal studies, we usually call F1 is the first the suspect, F2 is the second suspect, and up to Fn. So Fn is the data, okay, or files, or a description of the answer suspect. Right. So if the police department want to investigate or want to solve a crime, and so that they will dig out, right, a list of suspects, and they think that the person who committed the crime would be one of this suspect. Okay, so that because different suspects will be exclusive, right? They are individual, and exhaustive means that the police department think that this suspect. Okay, so that the person who committed the crime will be one of the person in here. Okay, and the second, so the probabilities P of F1. So based on the description of this suspect, each suspect has a probability to commit the crime. Okay, so that these are called a priori probability a priori probabilities of the N hypothesis. Okay, right? Just based on, for example, just based on the background or the history of each suspect, then the police department will assign probabilities for individual suspect to commit the crime. Okay, so that would be we call a prior probability before we use any evidence. Okay, before we use any evidence. Now, if we have an evidence called E, then the conditional probabilities of event EI given the evidence E are called posteriori probability of the N hypothesis given the evidence E. Given evidence E. Okay, so the police department should recompute, the probability to commit the crime after an evidence E is provided. Okay, so they should be able to compute this conditional probability. Okay, so and the computation of this posteriori probability, which is just the conditional probability of Fj given evidence E, would be this one. So by the base formula here, will be this formula. Okay, so you see that the computation of a posteriori probability is based on the a priori probabilities. Okay, this is a priori probabilities, as well as the conditional probability, of having the evidence E given the J's hypothesis. Okay, so you can see with different hypotheses, the police department should be able to evaluate that based on the background of each suspect, then the police department will evaluate the probability that an evidence will occur. Okay, so that and this is from the police department will have experts to be able to estimate these conditional probabilities, because this is based on the background of each suspect. Okay, so they're based on the criminal theory that they were able to evaluate this conditional probability, and then they should be able to find the posterior probabilities. Okay. Now, so after observing an evidence E, we choose. So we choose a hypothesis Fj whose a posteriori probability is maxima, i.e. we will find a suspect F sub j by using the following formula. We find the argument okay, so we have n suspect f1, f2 up to fn, and we find the maxima of these posterior probabilities. Okay, once we find that and we know which suspect achieve this maxima, so we take the argument here, and this is fj. Okay, and this is called the maximum a posteriori, in short MAP, maximum a posteriori decision rule. Okay, so this is a very important decision rule in many situations. Okay, in many situations. All right, so in my criminal explanation, we know that the hypotheses are just different suspects. But if in the communication engineering, the F1, F2, and Fn would be possible message to be transmitted from a transmitter to a receiver. Okay, to a receiver. All right, and so a person in the receiver, they want to find the signal which is transmitted from transmitter, and the E is just the signal that the receiver received. So based on the received signal, then people try to find the conditional probability of the J signal transmitted, given that the signal E is received. Okay? And based on the maximum a posterior decision rule, the people will decide that the transmit signal will be Fj if the a posterior probability of Fj given the received signal E is the maximum among all possible a posterior probabilities. Okay, and quite often that the computation of this condition probabilities were based on the base formula here. Okay, because in communication theory it is easy to compute this conditional probability. Okay, because given the transmit signal, in general we are able to find the conditional probability that the received signal is E. Okay, so this conditional probability will be easy to be computed, and the transmit signal before we receive anything, this is just we call the a priori transmitted probabilities. Okay, so this usually this a priori probability, okay, are known. Okay, so we know this a priori probabilities at hand. And then we can compute this ratio, which is just the condition probability of transmitted signal Fj, given that signal E is received. Okay, so there are quite many situations. And also in economics, the hypothesis here may be some possible patterns of the growth of a country or a region, for example, in next year, right? So that they will make up mutually exclusive and exhaustive hypotheses about the economical situation of the country in next year. Okay, and so that these possible patterns has a priori probability, which is just what? It's just a computation based on the history. Okay, and a new evidence or a new development in the economic world may change. Okay, may change the probabilities there. Okay, so this is very important probability to compute. Okay, so there are a lot of applications of Bayes formula in many different disciplines. Okay, many disciplines. Okay. Right, so we take a short break of 5 minutes.
Right. The next section is about independence. As we recall that independence is a special situation of conditioning. Okay, but before we make such a point, we will define independent events directly. So two events, E and F, are called statistically independent of each other if the joint probability of these two events, okay, is equal to the product of individual events. Okay, so if this is true, all right, there is a remark. If the probability of an event F is 0, then E is independent of any other event E. Oh, then F, sorry. Then F is independent of any other event E. Why? Why? The proof is here. All right, so we know that the intersection of E and F is a subset of event F. So this implies that the probability of the joint probability of E and F is less than or equal to the probability of F, but this is 0. Okay, and this inequality is from axiom number 1. Okay, this is from proposition. I think it's 2.4.1. Okay. All right. So that this is implies that probability of E intersect F, which is equal to 0. Okay, and because it's 0 and this is 0 times probability of E, so will be probability of E times 0. And so this is probability E times probability F. Okay? Because probability of F is 0. Okay. Alright, so if an event F has 0 probabilities, then this event will be independent of any other event. Okay, by our definition. Okay, by our definition here. Okay, so now we will examine quite a few properties of independence based on this definition here. Proposition 3.4.8. If E and F are two independent events, okay, then the conditional probability of E given event F is equal to the unconditional probability. And also, the conditional probability of F given event E is equal to the unconditional probability of F. Okay. All right, let's see the proof. Okay, because we define independence between two events in a symmetric way, right? So E and F are independent events. Okay, all right. So if we have this identity, then we have that identity too, right? Because by the symmetry, so it will be enough to prove the first identity. Okay, so now we consider two cases, right? Probability F is equal to 0. Okay, then by definition of conditional probability, we know that the conditional probability of event F given event the conditional probability of event E given event F is equal to the unconditional probability of event E. This is by definition in this case. So we already has this identity. Case number 2. This probability is positive. Now, so that we know the probability of E given F, which is equal to probability E intersect F divided by probability of F. Okay, this is by definition of conditional probability. Alright, but now E and F are independent, so their joint probability is the product of individual probabilities. Okay, and so we can cancel them. So this is P of E. Okay, again, we have the same formula. Okay, so we conclude that this conditional probability is equal to the unconditional probability. And by symmetry, all right, so we know that two. Okay. So if E and F are two independent events, then we know this conditional probability of E given event F would become to the unconditional probability. Okay. All right. So independence is quite a special situation of conditioning, because that in that case conditioning will take any effect, will not take any effect on the event E. Okay. And vice versa. Yeah. All right, and the other way, okay, if either the conditional this conditional probability of event E given event F equal to the unconditional probability of event E, or if we have this identity, right, either one, then E and F are independent of each other. Okay, so the proof is simple. That we know that probability of E intersect F is equal to the probability E say probability of F times probability of E given F. Okay, so that would be so this is the this is our multiplication formula, right? Okay, so by multiplicative E, okay, by multiplication rule. Right? So we know by multiplication rule, we can write this joint probability as the product of the unconditional probability of F and the conditional probability of E given F, or the product of unconditional probability of E and the conditional probability of F given E, either one. And you can see that if this is true, okay, then we can apply to here. Okay. But if this is true, then we can apply this to here. Okay. So when we apply this to here, we have PF times PE. Okay, and but when we apply this to here, if this is given, all right, then we apply to here, then we have PE times PF. So the result would be PE times PF. Okay, all right. So the joint probability of E and F is equal to the product of individual probabilities. Okay, and so this is independence. Okay. All right. So from these two propositions, so you can see that independent events means that this conditional probability becomes to be unconditional probabilities. Okay, right? So you are not clear that independence is a special situation of conditioning. Okay, very special situation. Now, I'll state a proposition stated in textbook. If E and F are independent events, then so are E and F complement. Okay, now we'll give proof. We know that E intersect F, E is equal to E intersect F is joint unit of E intersect F complement, because F and F complement become together form a partition of the subspace. Okay. So, okay, so we and okay. Right, so we have this and so now by finite additivity, we know the probability of E is equal to the probability of E intersect F plus the probability of E intersect F complement. So we have that. Okay, so this is from the finite additivity. Okay. Now, because E and F are independent, so this is PE times PF. Okay. Right? Because that E and F are independent. Okay, so we show here. Now, all right. So this one. So now the joint probability of E and F complement becomes P of E minus P of E times P of F. Okay, the difference here. Now we have a common factor P of E and the 1 minus P of F. Okay. But 1 minus P of F, it is the probability of F complement. Okay, so this is by proposition 2.4.2, I think, right? Okay, so now the joint probability of E and the F complement is equal to the product of probability of E and probability of F complement. Okay, so E and F complement are independent of each other. Okay, so this gives the proof of proposition 3.4.1. Okay, so when E and F are statistically independent, then E and F complement will be statistically independent. And the same statement, because E and F, the definition about independence is symmetric, all right, to F, to E, and to F, so are E complement and F, okay? Right. And the corollary E and F are independent, then E complement and F complement are independent. Okay. The proof is that we apply the previous position twice. So E and F independent implies E and F complement independent. Okay, so this is proposition 3.4.1. All right, and so this is implies. Now we fix this one as we said this is called G, right? It's an event G. Okay, and E and the G are independent, so this implies E complement and F complement are independent. So again, this is proposition 3.4.1. Okay. Right. So we start with a statement that E and F are independent, implies that E complement and F complements are independent. Now a question you may raise: if E is independent of F and is also independent of G, is it independent of F intersect G? Okay, so we know E and F independent, E and the G independent. Now a question is that is E independent of the joint event of E and F? Okay, and the answer is no. Okay, so please see example 3.4.E in the textbook. So you will see that a common example, right, in the textbook. Right, so up to now, we consider two independence events. So now we will generalize the concept of independence to many events. Okay, right. So we will address the definition. So we start with three events. Three events: E, F, and G are called independent. All right, so three together are called independent if P of E intersect F. Okay, so E and F are independent, so that we have the formula P intersect G is the product of P of E and P of G, and P of F intersect G is P of F and P of G. Alright, so the first condition is that they are independent in pair, okay? At least, so they are independent in pair. So we say E and F and G, these three events are independent if for these three here, they are independent in pair. And also, they are joint event. Okay, so we consider the intersection of E and F and G. This joint probability is the product of the three individual probability. Okay. All right. So three events are independent. It's more than they are independent pairwise. Okay, more than that, because we have one more additional requirement here. Now, so the definition of the independence among three events is much stronger than pairwise independence. Okay. All right, and we make a point: if E, F, and G are independent, then E will be independent of any event formed from F and G. Okay. Formed means that from F and G, which means that we can use the not and and or, okay, to form new events. Okay, so any events formed from E and G, there are a lot of them. So let's say F, G, F complement, G complement, okay, and F intersect G, F intersect G complement, F complement intersect G, F complement intersect G complement. Okay, so they are about them. F union G, F union G complement, F complement union G, F complement union G complement. Okay, so you can see there are a lot of events which can be formed from F and G, right? So just give you a list about that. Okay, so you can see that, right? Okay, and so let me take, for example, before we prove a general theorem, I'll take an example, okay? So we take, say, F union G, okay? This one. So this event is formed from F and G. And we will show that event E and this event are independent, okay? All right, so we will compute them, okay? So we compute P, E intersect F union G, okay? So we want to show that the probability of E intersect this union is equal to the probability of E times the probability of F union G, right? Right. All right, so we see that. So this is probability. And the intersection, by using the distributive law, so this is E intersect F, union E intersect G. Yeah. But the union is in general not a disjoint union. Okay? So we cannot apply the finite additivity. Instead, we apply theorem 2.4.3, which is just the simple inclusion-exclusion formula plus P minus P okay? So this is proposition 2.4.3, which is just the simple inclusion-exclusion formula. Now, because E, F, and G are independent, so we know that they are at least pairwise independent. So the joint probability of E and F becomes the product of PE and F, and the joint probability of E and G is the product of E and product of G. But we look at here, this E intersect F intersect E intersect G, which is E intersect F intersect G. Alright, so now this is the joint probability of EFG. Alright, and so we can apply here. So this is minus P of E, P of F, and P of G. Okay, so we have these three. Okay, now so in here we have common factor P of E. Okay, we have common factor P of E, and this is P of F plus P of G minus P of, but P of F and G is P of F intersects G. Okay? Okay, because up here, because F and G are pairwise independent, okay, so this product actually is equal to this one. And then we know this is exactly the inclusion-exclusion formula of P of F union G. Okay, so we can apply the proposition 2.4.3, which is just the simple inclusion-exclusion formula. Okay, and so we proved it here, right? Okay, so now this is finalized. E and F union G are independent. Okay, so this is a simple demonstration to show that when E, F, G, these three events are independent, then E will be independent of any event formed from E, F, G. So right, we just take this one. If you can, as an exercise, you can take, for example, maybe this intersection or this union, right? And to show that E is independent of this event. Okay. All right, now, we talk about, we give definition of three independent events. Now, we generalized to a finite number of events. Right, so n events E sub I from 1 to n are called independent if for, okay, if we take R indices and these indices will be different, so we say I1 is, let's say I2 is up to IR, but in between 1 and n, okay, so, right, so we have n events, but we take R events from an event. Then, E sub I1 intersect E sub I2 intersect E sub IR, okay. Alright, so their joint probabilities is equal to the product of individual probability. Okay, so how many identity we have here? Okay, so we see that we have n select 1 plus n select 2 plus n select n. Okay, but in general, so which is equal to R from 1 to n, and select R. Okay, equations. When R equal to 1, when I equal to, we just select 1. So probability E sub I equal to probability E sub I would be trivial. Okay, so they are just trivial. That's fine. But that's okay. And so this number is 2 to n's power minus 1. Okay, so we have actually that many. So if we exclude the trivial case, maybe we just say or. But if we put that, then you should know n is at least 2. Okay, n is at least 2. Okay, and in that situation, you can just eliminate the trivial one, so that the equation will becomes to be 2 to the n's power minus 1 minus n. Okay, so we have 2 to the n. So power minus n minus 1 non-trivial equations. Okay, so it's a lot, and you see, it's a lot. When n equals 3, right? So 8 minus 3 minus 1 is 4. So we have 4 equations here. When n equals 3, we have 4 equations. But in general, if we have n events, alright, for example, when n is 10, so if we have 10 events, and we say these 10 events independent, then we must have how many equations to satisfy? About 1,000 more, right? More than 1,000 equations. Okay? So when n is 10, then you have more than 1,000 identities. Alright? Identity here. So it's a lot. Alright, so when we make assumption that n events are independent, you mean a lot. Okay, you mean a lot because there are a lot of equations has to be satisfied. So this is a very strong situation. Okay, so you have to know that. And from this definition, it is clear. Okay, if n events E1, E2 up to En are independent, then any k is between 2 and n minus 1 of them. So you just select part of them, okay? Maybe take 2 or 3 of them, or n minus 1 of them, okay? Are independent too. Okay, right? So a collection of n events are independent. Then any subcollection will also is independent. Okay, so because this is so strong. Okay. All right, and now I will give a proposition. 3.4.d. N events E1, E2, up to En are independent. Okay, if and only if the probability of joint probability B1 intersects B2 up to intersects Bn is equal to probability of B1, probability of B2, probability of Bn, where Bi is either EI or EI complement for all I from 1 to n. Okay? So in here, because Bi is either EI or EI complement, so there are 2 choices, all right, for each Bi. So that here we have 2 to the nth power equations. Okay, so here we have equations here. In the definition, we have 2 to the nth power minus n minus 1 equations, and the equivalent condition. All right, so then we have 2 to the nth power equations. So they have the same order. Okay, they have the same order. Yeah, because compared with the exponential function, the linear function can be neglected, okay, if n is big enough. So you see that this system of equations does not ease our justification problem, because the complexity would be actually the same. Okay, because the number of equations needed would be 2 to the nth power. Okay, but this formulation, this identity will give us a lot of advantages in develop the properties of independence events. Okay. Okay, so that, and of course, in some situation, if you want to verify that n events are independent, then you can use the identities here to do the justification. Because every time you take n events, but each event is either EI or EI complement. Okay, so you can do the argument that if we can show this identity, then you are sure that the n events are independent. Okay, so that this is a quite a nice proposition to have, and the proof is actually long, takes 2 pages. All right, so I will not give the proof, but will send you a note, all right, for you to read. Okay, otherwise the proof will take more than half an hour. I think probably 1 hour. I'm not so sure. Okay, but the important thing is that we have this nice identity here. Okay, because that's every time we always consider n events. Okay, every time we consider n events, and the freedom is that for each piece of I, we can select either EI or the EI complement. Instead of from the definition that they involve different number of events, okay, from the n events there. Okay, so I will see proof. Given in Hangout or given a supplemental article. Okay. All right. So I will take this proposition, okay, to do the following development. And my purpose is to show effect like this, okay? Before that, we need a proposition. The smallest sigma sub x bar of f, which contains n events E1, E2 up to En in F. Okay, is the collection of all possible unions of B1 intersect B2 intersect Bn, where Bi is either EI or EI complement for I, okay, in between 1 and n. Okay, so before I take the example, so I will show to you an example. Okay, so let E1 and the E2 be two distinct events such that E1 and E2, so none of them are ambisect over the total event. Okay, and now, so we can think about that. This is the X, that's the total event, and alright, so here this is E1 and the E1 complement. Okay, and here we have the E2 and the E2 complement. Okay, and so this part is E1. E1 intersect E2, and here is E1 complement intersect E2, and this one is E1 intersect E2 complement. This is E1 complement intersect E2 complement. Okay? Alright, so based on E1 and E2, okay? Okay, now the smallest sigma algebra, subalgebra, we say G of X, which contains E1 and E2 X here. Right, so that either the empty set, okay? Empty set. Okay, and we see that we try to find the atomic events, okay? The smallest, the minimum events, which is non-empty, but the minimum one, but created from E1 and E2, right? So what can we do is we can take the complement, intersection, and union, But to find the smallest event, we see that the smallest possible event would be this 4. Okay, so this E1 intersects E2, E1 intersects E2 complement, E1 complement intersects E2, E1 complement intersects E2 complement. So these 4 will be atomic events. Okay, as you can see from here, they are atomic events. So in G, so that these 4 atomic events in G, okay? There may not be atomic event in F, but for G, because G is the smallest sub-algebra, all right, containing E1, E2, so there should be generated, any member in G should be generated by E1 and E2 by doing the complement, the intersection, and the union. All right. So that if we want to find the minimum one, the atomic one, then this 4 will be atomic events in G, and then the other event will be the union of them. So that I'm sorry. So E1 complement. So you can see that E1 is actually, okay, I will see. So E1 is actually E1 intersect E2 union E1 intersect E2 complement. Okay. So these four atomic event will be the building block of G. Okay, this should be the building block. So that E1 intersect E2. This building block and this joint union with the second building block, they together it give you E1. Okay, and also E1 complement is also equal to E1 complement intersect E2, this joint union, E1 complement intersect E2 complement. Okay, and similarly E2 and E2 complement. Okay, so you have that. Right, and you have a little more. Okay, for example, E1 union E2. Okay, and E1 union E2, and E1 union E2 complement, and E1 union E2, and E1 union E2 complement. Okay, and finally you get X. Okay, so that would be 16. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13, but 14. So 2 left. Let's see. Oh. Oh yeah. So we're missing 2. Okay. Let me see that here. E1, E2, and also this 2. Okay, and that 2. So that would be E1 intersect E2, the joint union of E1 complement intersect E2 complement, and also E1 intersect E2 complement, the joint union E1 complement intersects E2. Okay, all right. Okay, and E1 E2, and E1 union E2 complement, E2 complement union E1 complement E2, E1 complement union E2 complement, and finally S. Okay, and so you can see that there are 16 members in G. There are 16 members in G. Okay. Okay, so in this case, you see this is 16. Okay. And this is actually 2, 2, 2, 2. Okay. All right. So so that so to prove so the collection of all possible union of these intersections, which means that this kind of events will become to be the building block of the smallest sigma algebra. Okay, so there should be the building block there. Okay, and so that BI is either EI or EI complement. So at the most, we have 2 to the nth power building blocks. Okay, 2 to the power building blocks. Okay. So before we give a proof, we make a remark. The smallest sigma algebra of F containing E1, E2 up to En in F will be called the sigma algebra. The sigma algebra generated by E1, E2 up to En, and denoted as F of E1, E2 up to En. Okay. And also another remark, proposition 3.4.E says that the collection of B1 intersect B2 such that BI is equal to EI or EI complement, and also we require that this is not equal to the empty set, and with Bi equal to Ei or Ei complement. Okay, because it's possible that the intersection becomes to be empty set. Okay, it is possible. So that we just collect all events formed in this way, but which should be non-empty set. Okay, so any such intersections which is non-empty, and B sub I is either Ei or Ei complement. Okay, this collection is the collection of all atomic events in the sigma algebra generated by E1 up to En. Okay, so they are all atomic events there. Okay, and we have shown that every event would be if this is sigma algebra, every non-empty event in F will contain an atomic event. Then every event will be a union, a countable union of the atomic events in C here. And so it is clear that the size of C means the number of atomic events in this sub-algebra, okay, generated by E1 up to En is less than or equal to 2 to the nth power. Okay, to the nth power, because each Bi has two possible choices, either Ei or Ei complement. Okay, and so here we have 2 to the nth power such kind of intersections, but some of them will become to be the empty set. So we have to exclude these empty sets. Okay, and so at most we have 2 to the nth power at most, but it around, all right, it about 2 to the nth power, maybe some amount less than 2 to the nth power. All right, but we know that at most it is 2 to the nth power, and so 2 to the nth power is still a big one. Okay, and so that's and okay, and by this is atomic events, and also by proposition 3.4.E, because with the subalgebra generated by E1, E2 up to En is a collection of all possible unions. So we use the atomic event to build, because atomic events are disjoint from each other, and then so you can use that to build up. All right, so to build up the every member in the subalgebra. All right, so that so an event in this generated sigma subalgebra would be a union of atomic events. All right, and good, so that each atomic event can participate in this union or not. So that so we have that the F so the size of this generated sigma subalgebra will be equal to 2 times the size of the collection. Okay, the size of the collection here. And because the size of the collection of all atomic events is upper bounded by 2 to the nth power, so this would be equal to 2 to, sorry, okay, the nth power there. So the upper bound is 2 to the nth power. It's a huge number. Okay, it's a huge number. You can see that. Okay, so you can see before we prove the proposition 3.4.e, you can see that we have know that the generated sigma subalgebra F here is 1. Okay, and right. So the important thing is to show that this collection give us all atomic events in the generated subalgebra. Okay. Okay. Right. Okay. Let's see. If I can't finish the proof, I will continue the proof next Tuesday. Okay. So we let T to be the n-tuple of events, okay, such that the BI is equal to EI or EI complement for all I from 1 to n. Okay, so we just form n-tuples, okay, from n-tuples, and you can see that the size of T will be 2 to the nth power. Okay, so there are 2 to the nth possible, 2 to the nth power possible n-tuples here. Right, now for two distinct n-tuple B1, B2 up to Bn, and B1 prime, B2 prime up to Bn prime in T, there is one I, okay, such that Bi complement is the Bi prime. Okay, sorry. So Bi prime will be the Bi's complement because they are different. So these two n-tuple are different. So at least the one entries, say B sub I, the i's entries are different, right? So Bi prime will be different from Bi. But as we know, in the nth entries, you have only 2 possible choices, either EI or EI complement. Okay? So if they are different, if Bi prime is different from Bi, then Bi prime must be the complement of Bi. Okay? So that we have this important, okay, fact. So that if we take the intersection, all right, so that the intersection of this n components and the intersection of this n component B1 prime, B2 prime intersect x Bn prime. Okay, this intersection, and we take the intersection of them, this becomes to be the empty set. Okay, this becomes to be empty. Why? The reason is here. This is contained in Bi intersect Bi prime, and this is empty set. Okay, because this intersection is contained in Bi, and this intersection is contained in Bi prime. Okay, so this is a subset of Bi, and this is a subset of Bi prime. Okay, and so this intersection will contain in the intersection of bigger set. But these two bigger set, Bi and Bi prime, is the empty set because the Bi prime is the complement of Bi. All right, so we know that they are. This intersection is the empty set. Okay, all right. Now, also, we take the union such that B1, B2, up to Bn in T, okay, of all of their intersections. Okay, but so for each n tuple, there is a corresponding intersection here. Okay, so we have intersection, and we take the union of them, and this union should be disjoint. Why? Because we have shown that for different n tuples, their intersection will this kind of intersection will be disjoint from each other. Okay. All right. So this should be the disjoint union. Okay, disjoint union. Okay, and we found that this is actually the intersection of EI union EI complement. Okay, so this is the intersection of EI complement. Okay, so it's easy to see from here to there because that the intersection has the distributional here. Okay, and so it's just like this one because intersection of the union. Okay, and so by distributional that this is become to the union of the BIs, and the BI can be EI or EI complement. Okay, so this is the same. Okay, and but the disjoint here, this is X. Okay, so every union here is the total event. All right, so you intersect X with itself n times. So this is X. Okay, so now, so that's the collection B1 intersect B2 intersect up to intersect Bn such that the n-tuple in T. So this one of events in F, all right, is a partition. It's a partition of the sample space. S. Okay? So now we find a partition, and in this partition, some members may be empty sets. Not every member not empty, okay? Right? But some member will be the empty set. So that's why in our remark we have to in here we have to collect all non-empty members in this collection. Okay, non-empty members. Okay, so we have a partition already here. All right, now we let G be the collection of all possible unions of just like we described of B1 intersect B2 intersect Bn with B1, B2 up to Bn in T. So i.e. G is here the union of B1, B2 up to Bn in W of the B1 intersect B2 such that W, okay, is in the power set of T. All right, so W just a subset of the T, right? The set T here. Okay. For example, if W is the empty set, so this is the empty union. All right. So this member will be the empty set. Okay, the empty set there. And if W is equal to T itself, then of course I have to say this is the disjoint union. Okay. So if W is the capital T, then this disjoint union will be the sample space S. Okay, this is the biggest one. Okay. Okay. So this is all possible unions here. Okay. And because they are disjoint, so we use these intersections as building blocks. Okay, especially the rows non-empty intersections. Okay, so basically they are building blocks, even though some of them will be the empty set. Okay, but that's fun at this moment. Okay, so we can still consider these intersections, even though the result would be the empty set. Okay. So anyway, so G is just the collection of all possible unions. Okay, here, just like we described in the proposition. So we have the collection of all possible unions here. Okay, all possible unions. And so the next job is to show that this collection is the smallest sigma algebra which contains these n events. Okay? So we have established or we have described this collection, all right, explicitly. Okay? So this is, so all the the argument up to here is to establish a collection G here. Okay, a collection G here. So our final job is to show that this collection is indeed the smallest sigma subalgebra. All right, containing E1 up to En. Okay. Okay. So I think I to be continued next Tuesday. Okay. So I stop here.